let's go through lab 17, which is the lab in which we build our own homemade op-amp. And we have borrowed the key ideas of this lab and some of the implementation from Tom Hayes' course. So you could check that out, Tom Hayes' excellent book, Learning the Art of Electronics, published a couple years ago. So we have adapted the numbers here to work with the EE board. So we have only plus and minus 9-volt power supplies instead of the plus and minus 15 we usually use in the classroom. So I've changed some resistor values. So these have been reduced to 5K, and this was reduced to 5K. So these are the collector resistors and the tail resistor. Also, the lab assignment does not tell you to include this collector resistor. I'm putting it in temporarily so we can just remind ourselves what it does. Also, here's something we missed when we did lab 16 at first. So pin 16 of this CA3096, this is 3096, it's a 16-pin dip. Don't confuse it with the CA3086 14-pin dip that we used in the previous lab. So this contains 3 NPN and 2 PNP transistors on one piece of silicon. Pin 16 is a substrate pin. It wants to be connected to the lowest voltage in the circuit. So we want to connect that to minus 9 volts. Otherwise, we get sort of unwanted diode connections that will cause surprising effects. Okay, so this is our differential amplifier. We studied this in the last lab, so it's a quick review. It's basically 2 common emitter amplifiers side by side and connected in such a way that we amplify the difference between these 2 inputs. In fact, I guess if you call this input A and you call this input B, then the output will be, let's see, I think it must be A minus B. I think the output will be A minus B. Because each one of these common emitter amplifiers is inverting. So, well, A minus B times the gain factor, right? Okay, and then we can, let's look at the quiescent state of this amplifier. So we're assuming that our 2 inputs normally rest near ground. So if the transistors are active, then these 2 emitters will be a diode drop below ground, and then there's some very small voltage drop across these 100-ohm emitter resistors. So this point, well, just roughly this point above the tail resistor will be basically a volt below ground. So that's minus 1, and then here's minus 9. So there's a difference of 8 volts across this tail resistor. So this current through the tail resistor should be about 8/5 of a milliamp. And dividing by 5 is like multiplying by 2, so 1.6 milliamps. So then half of that flows through this collector, half of that flows through this collector in the symmetric state. So each one of these quiescent collector currents is 8/10 of a milliamp. That means our little Re, the effective resistance of the base emitter junction as seen from the emitter, dynamic resistance, is 25 millivolts. That's that thermal voltage, Kt over Q. 25 millivolts divided by the collector current, which is about 31 ohms. Then we can use the expression we derived last time for the differential gain, Rc over twice Re plus little re. So that gives us 5 kilo ohms over twice 131 ohms. That's about 19 for the differential gain that we expect. Then remember the differential voltage is Vin plus minus Vin minus, which I think means Vin A minus Vin B in this configuration. And then the common mode gain should be minus Rc over twice R tail plus big Re plus little re. So that's minus 5 kilo ohms. And then there's twice 5 kilo ohms downstairs and 131 ohms. So that's basically minus a half. So this 131 ohms doesn't matter much compared to 10,000 ohms. And then remember that the common mode voltage is the average of the 2 inputs. So there's this funny factor of a half here in the definition of the common mode voltage. Then I guess another thing we can look at is the quiescent voltage of the output here. So the resting place where V out rests. So it's going to be VCC minus IC RC, right? VCC minus IC RC. So that's 9 volts minus, this is 0.8 times 5. So 0.8 times 5 is 4. 9 volts minus 4 is 5 volts. So we should see a quiescent output voltage of 5 volts. And then, now the assignment does not tell you to put this other collector resistor here. I put it here so we can see just see what it does. What it will do is we'll get two complementary outputs. So you can call them out and out bar if you want. So this output will just do the opposite of what this one does with respect to the quiescent value. This one goes up above 5. This one will come down below 5. So we can see that. All right, so I think that's it. So I built this circuit. And I put here in green the pin numbers, so 1, 2, 3, 4, 5, 6. So let's take a look at how it is assembled. So here are my two waveform generator inputs. Here, these two blue wires. Okay, so I have AWG channel 1 going into pin 1, and I have AWG channel 2 going into pin 5. Then I have scope channel 1 probing pin 6, which is our main output, and then I have scope channel 2 probing pin 3, which is our secondary output, which should have the opposite, whose AC component should have the opposite sign. And then, let's see, there should be nothing else at pin 1. Pin 2 should have 100 ohms, and pin 4 should have 100 ohms, and they should meet at this point that goes down through this tail resistor to minus 9 volts. So that's happening over here. So here's pin 4 with our 100 ohms, pin 2 with our 100 ohms. They all meet in this little column, just one space to the left of the IC. And then this is our 5K resistor down to minus 9 volts. And then from pin 3 up to plus 9 volts and from pin 6 up to plus 9 volts, I have these two collector resistors, which are both 5K resistors. That's this guy and this guy. Okay. Then let's take a look at the waveforms. Okay, the first thing to notice is that the resting place for both of these signals, the quiescent value, is at 5 volts. It looks like, well, the cursor is at 5.04 volts, but basically it's at, I can't tell if it's 5 or 5.04. So it's basically 5 volts as we expected for these quiescent values for the outputs. And then notice that the two outputs, their departures from 5 volts go in opposite directions as we expect. And then what am I sending in for input signals? I'm using these two channels. There's a 20 millivolt amplitude, and they're 180 degrees out of phase. So I'm putting in a 20 millivolt sine wave at 1 kilohertz from channel 1, and I'm putting in a 20 millivolt sine wave at 1 kilohertz with the opposite phase in channel 2, and they're synchronized. And, well, and as usual, the supplies plus 9 and minus 9 are on, and nothing else is on. So then if we go and look at it, so that is a 40 millivolt differential signal, right? So we have V diff is 40 millivolts. So then let's see if we get something like 19 times that for the output. So when you want to measure a small signal with a big output, well, we could, with this scope, we could explicitly subtract, although we might eventually run into the limits of the digitizer. So it's convenient to switch to AC coupling. So we're going to move the little scope wires on the EE board over to AC coupling. That basically sticks a big capacitor in series with the scope probe, and so then the DC signal is blocked, and you can look more closely at the time varying part. And then we will increase the scale. Let's see, there's 500 millivolts per division. Okay, 200 millivolts per division. It's a little noisy. That's a little annoying, but we'll deal with it. So we have, and I'm using this cursor. I guess this cursor is set up to look at channel 2. Actually, I'm going to change it so it looks at channel 1. Because I think we're, in general, going to be doing our measurements from channel 1. Okay, and then this cursor, we're going to set this cursor up to look at channel 1. You could use the amplitude function, but I don't know how the amplitude function deals with noise. So I prefer just by eye to stick. Oh, by the way, Joe's told me this amazing trick. So if we trigger here at 0 volts, I can put a hysteresis of, let's say, 200 millivolts. So it kind of makes a Schmidt trigger-like trigger. And you notice that the triggering is much more stable this way. So use a little bit of trigger hysteresis. So I like to stick the cursor right in the middle of the noise blob. And it seems like, okay, we have plus 485 and minus 490. So that's basically 0.49 amplitude. Oh. No, it's half of 0.49 amplitude, right? So, no, it is. It's 0.49 amplitude. That seems smaller than a gain of 19, doesn't it? Let's try. Yeah, because that's a gain. Well, that is a gain of, that's just a little over 10, right? So we have 0.49 divided by 0.040. That's a gain of 12. That, I actually got, when I measured this circuit yesterday, I saw a gain of 17 or 18. And then in Circuit Lab, I saw 19. In Circuit Lab, you can use a really tiny input signal. So the circuit has kind of a nonlinear response because of the effect of little re. So little r, oh, you can't see that. Little re tends to, because little re changes as the collector current goes up and down, as the input goes up and down, it gives you some nonlinearity. So you get a measurement that agrees with the calculation if you use a very small input signal. Let me try making this 10 millivolts. So the trouble with making the input signal too small is that then we have to deal with, and I don't think this will do anything, but sometimes I just like to stop and run. Okay. Oh, and then we can go to 100 millivolts per division. So you make the input signal too big, and you have to deal with the nonlinear response of the amplifier, so it disagrees with your calculation. You make the amplitude too small, and you're stuck in the noise. And I don't know what the source of this noise is. Sometimes it's the amplifier itself oscillating. Sometimes it might be sometimes it's parts of the instrumentation. Okay, so here we have a 20 millivolt differential amplitude, and we see, okay, right, 240 millivolts. So again, we see a differential gain around 12. That is kind of disappointing because yesterday, when I measured the same thing, I got a differential gain much closer to 18. Let me just make sure, well, see, we're not quite off by a factor of 2. If you're off by a factor of 2, you could wonder if the issue is like that half of the amplifier isn't working. Let me just wiggle the wires a little bit. Well, okay, I found after wiggling these emitter resistors a little bit, I think I had some of the leads touching each other. So I think I might have been shorting things out a little bit. So I'm back to a 100 millivolt differential amplitude. So I have 50 millivolts on one end and 50 millivolts on the other end, out of phase with each other. And then I see about a 1.6 volt differential, output amplitude. So that's a gain of 15 or 16. Differential gain of about 16. Yeah. And okay, so I think I had some inadvertent connections down here with the emitter resistors. Okay, so I did see more like 17 yesterday. In Circuit Lab, I saw more like 18 or 19, but I guess good enough. Now let's do common mode. So the way we can do common mode is we can just move, just have both channels look at the same AWG input. So I'll just move them both to the first AWG input. And okay, it looks like we see an AC signal which is a lot smaller. And let me just go back over to WaveGen. Let me make the amplitude like 10 times as big here. So let's make it 500 millivolts. Well, actually, let's make it 1 volt common mode. So that's, I guess I don't have to change the other one. I'm only using one of them. I'll change them both. So we're going to have a 1 volt common mode signal. And what do we get? Okay, and we see basically a half volt. Oh, and this is interesting. So in the common mode, which of course we're trying to reject, the two outputs do the same thing. It's in the differential mode that the two outputs do opposite things. That's kind of neat. So of course we don't really want a common mode. So we're going to make the common mode gain even smaller in a moment. But okay, so we have half a volt output for a 1 volt common mode signal. That's consistent with our prediction of a half, minus a half. Oh, can we find the minus sign? I guess if we really wanted to, we could find the minus sign. Let's see. We can we do that? Here, we can look at one of these inputs. And there you see the minus sign. Ha! So it's the opposite phase. Cool. Okay, so we have our minus 1/2 common mode gain. So the next thing we're going to do is, I think we're going to use a current source to get rid of the tail resistor. So let's go do that on the board. Okay, our next step is to replace this tail resistor, which you can already see is gone, with a current source. And the reason we do that is that, remember that a good voltage source has an output resistance that's very small, ideally 0. And a good current source has an output resistance which is very large, ideally infinity. So for a good current source, first of all, for a good voltage source, as you draw more current from the voltage source, the voltage does not change, right? So a good voltage source, we have dV out with respect to dI out is small. Okay, and this quantity is called the output resistance of the voltage source. So for a good current source, we have dI out, dV out is small. So for a good current source, this is unreadable. dI out, dV out, yeah. So for a good current source, as you move up and down the voltage here at the output of this current source, right? So this current source, the output of this current source is up top, so it's kind of pulling current down to minus 9 volts. So in fact, we can even make this look like a current source symbol. So as you move this voltage at the output of the current source, which is the collector of this transistor, up and down, an ideal current source would not have its current respond to that at all. So the reciprocal of the output resistance should be small for a good current source. That means a good current source should have a large output resistance because the output resistance is dV out, dI out. So you want the reciprocal of dV out, dI out to be small for a current source. You want dV out, dI out to be large. You want dI out, dV out to be small. Okay, and the reason for that is that we can actually get, so it'll turn out for our current source that R out, which is dV, we can call this the capacitor here. Anyway, dV out, dI out, which in this case is, the derivative of this collector voltage with respect to, we can call it this tail current. is on the order of, it's not even on the order, it's pretty close to 2 mega ohms, okay? So that means we get to replace this tail resistance here. It was 5 kilo ohms, now it becomes 2 mega ohms. So when we do that, now instead of having a common mode gain of -0.5, we have a common mode gain of something like minus 0.001. It's like on the order of 10 to the minus 3. So that really kills the common mode gain. And how, by the way, if you wanted to do this with a 2 mega ohm resistor, suppose you just wanted to take the tail resistor and replace it with a 2 mega ohm resistor. If you did that, see, we want to flow 1.5 milliamps. If you want to flow 1.5 milliamps through a 2 mega ohm resistor, you would need minus 3,000 volts down here. So that's not feasible. We don't want to use minus 3,000 volts for our power supply across a 2 mega ohm resistor just to get 2 mega ohms tail resistance here. Instead, we can make a current source, which with a modest, looks like we had 6 volts across it from its collector to its emitter, or from its collector all the way down to, or it's like 8 volts from its collector all the way down to the power supply. We can get this 2 mega ohm dV/dI, right? So that means it's reciprocal dI dV is, what is that? It's on the order of 10 to the minus 6 mhos, or reciprocal ohm. Okay, let's talk about this current source for a second, and that way we want to get moving. First of all, let's make sure we got the right values for the current source. So this is actually the current source that was drawn in the original lab, except that this was a 2K resistor. We changed it to 1K, and that turns out to work quite well. So if you look at what's happening at the base, remember we usually analyze these circuits starting out with the assumption that the transistor is active and that the base current is negligible. And then you can see whether you derive a contradiction from it being active, and you can see whether the base current turns out to be non-negligible, or you can account for it. Okay, so if this base current is negligible, then the voltage at the base is, see, this is just like a voltage divider with 3K to ground and 1K to minus 9 volts. So it's like basically we have minus 9 volts, and then using the voltage divider equation, right, we have 3 over 3 plus 1. So we have 3/4. So that is minus 6.75 volts. So this is minus 6.75 volts at the base, and this is a diode drop lower. So that's minus 7.45 volts. Meanwhile, this is minus 9 volts. So minus 9 is 1.55 volts lower than minus 7.45. This is a 1K resistor. So that's 1.55 milliamps. That's pretty close to the 1.6 milliamps we had across the 5K resistor before. So that's so we say, okay, that's good enough. We wanted 1.6 milliamps. We got 1.55 milliamps. Good enough. Then you say, well, how big a resistor does that appear to be? So for a single transistor current source, which we usually draw sort of like this, I mean, you might use different voltages here, but this is how it's drawn here. I found a small signal derivation on a set of Georgia Tech course notes. And I took their expression. So I'm still learning how to do these small signal models myself. So I haven't, I got partway through. I didn't get all the way through trying to redrive this. But I took their expression and I said, well, let's kind of use the, let's try to bring out the most important terms. So I said, let's make the expression valid in the limit that beta is pretty big, and that this emitter resistor is reasonable size, and so on. So for so this is kind of an approximation to their result, but it's good for, I think it's good for plausible values you would choose here. So upstairs, you have this thing's called the early voltage, And then this is the voltage from collector to emitter for the transistor. This turns out not to be too important. So it's like the early voltage is a parameter of the transistor. It's about 75 volts for our 3904 transistors. This is the collector current. So here we have 75 volts, and then VCE, right? So this is about 2 volts. Well, it's a little less than 2, but this is roughly 2 volts, and then this goes about 8 volts. You have about 6 volts, maybe it was 6.5 volts. Anyway, so this is 81 volts upstairs, and then you have 1.55 milliamps downstairs. And then, and I think this factor all alone is what you would get if you made a current source that had no emitter resistor there. But the presence of the emitter resistor then gives you this, it makes, right, and this number is usually on the order of hundreds of kilo ohms. Let me see. We could work that out, I guess. So 75. Oh, actually, this is, no, it's not, yeah, this is like on the order of, actually less than that. 75 by 111. This is probably like 50, yeah. This is like about 50 kilo ohms. Okay, so that's not great. I mean, it's better than 5 kilo ohms, but it's not great. But there's this negative feedback. The negative feedback, oh gosh, I'm digressing again. The negative feedback is, suppose the load current tries to go up. If the load current tries to go up, that brings the emitter voltage up a little bit, which squeezes down on VBE, which then brings the collector current here down. So that's negative feedback. Or suppose this collector current tries to go down. If this tries to go down, then this emitter voltage will go down, which increases VBE, which then has the effect of increasing the collector current. So it's like it's negative feedback, which is protecting, it's kind of stabilizing this collector current. So that's basically what this factor is doing. So this is 1K, our emitter resistor, and then this is little re, and then this is the emitter resistor plus these two things in parallel, all divided by beta. And so if you plug in, this is like 16 ohms for 1.55 milliamps. There's one other term I neglected, which is like typically on the order of 10 ohms, which is like there's actually a series resistance at the base. It's not R pi. There's another additional series resistance at the base that's sometimes included. It's like on the order of 10 ohms. Okay, so I didn't include that. Okay, and then 1 over beta, and this is RE, 1 kilo ohm, and then R1 parallel R2 is 3/4. So you have 3 parallel 1 is 3/4 of a kilo ohm. So then all this stuff together gives you about 2 mega ohms. And I actually checked this in Circuit Lab, and in Circuit Lab I got like 2.05 mega ohms or something. So it actually, seems to agree with the Circuit Lab model. So far so good for this approximate formula, which I really want to learn how to derive. So I've been going through Cedra and Smith's discussion of small signal models, the hybrid pi model. So I hope I learn how to derive this soon. Okay, anyway, so the effect of this tail resistance, it shouldn't have any effect on the differential gain, but the common mode gain should now go from -0.5 to like -0.001. So I think we can see that. So if we, let's see, I think, oh yeah. So I can show you on the circuit here, this is this external 3904 transistor, NPN transistor. And I wired it up with these 3 resistors. And then its output at the collector is this little blue wire, which is now going to where these two, this pair of 100 ohm resistors meets. So this point now goes into that collector. Okay. And then we can look at the waveforms. And actually, it was fun. When I first plugged this in, you could see the common mode signal disappear. I guess you don't get to see that because I made that change when you weren't looking. But if we go over to WaveGen here and well, this is already a 1 volt amplitude. That's pretty big. We could try making it, let's see, I guess we could try a 5 volt amplitude. Then you see, it's like you still can't see it. Well, this is 500 millivolts per division. I guess we could try to go down to 50 millivolts per division. It seems like it's just too small to see. We don't really see any. So I would say that the common mode gain is now too small for us to measure. So that's cool. Meanwhile, if we go to WaveGen here, and let's go to something reasonable again, like 100 millivolts. Actually, let's do 50 millivolts and 50 millivolts, because that's easy. It makes the math easy. Here's 50 millivolts. Here's 50 millivolts. I want to show you the differential gain basically hasn't changed, I hope. Okay, we'll go back over here, and then instead of plugging both inputs into the same function generator, I'm going to plug one into one function generator, one into the other. Okay, it seems like we have a much bigger signal here, and we can go to, here's 500 millivolts per division. Okay, and it looks like our amplitude for this differential signal is so it was a 100 millivolt differential signal, and we see like 1.78. So that's actually a differential gain of about 18. Oh, it's interesting. All right, so anyway, differential gain like 18, not too far from our prediction of 19. And then the common mode gain, too small to measure. Okay, now I guess one more thing we could do is, let me show you that this resistor doesn't matter. It was kind of nice to have it in the derivation because it makes the symmetry argument more obvious. But we can take this resistor out. If we're not using this second output, then we don't need this resistor. And the lab assignment never called for it in the first place. I put it there just for fun. So let me take that out. Let me see if I take it out in a way that you can see it. So that was coming from pin 3. Here's pin 3 going up to +9. So if I just rip this out, then that's interesting. Okay, and then we want to replace it with by the way, my first CA3096 transistor array that I tried yesterday was broken. It had, and these chips are kind of expensive. So there were 2 of them in my kit, so I had to use a second one. So it probably wasn't such a good idea that I didn't turn off the power when I made that change, but I'm trying to protect this one because I only have one working one left. Okay, so I removed that second collector resistor, and it didn't make any difference, except that the second output, of course, no longer works because because now the collector voltage is just 9 volts, and we're looking at it with an AC coupled scope channel, instead of it going up and down with instead of it being VCC minus ICRC. Okay. Oh, maybe you couldn't see what you couldn't see what I was pointing at. Oh, that's terrible. Oh no. Haha. Yeah. So we took this resistor out. Right, so we connected pin 3 straight up to +9 volts. Okay, and you saw me do it over there. What's next, I think, is we're going to remove these 100 ohm resistors. Let me just double check that. Yeah, so the next thing we're going to do is we are going to remove these 100 ohm resistors, and that's going to make the differential gain even a little bigger. So these things will no longer be there. So that gives us more gain, but a price we pay is less linearity. Hold on here, let me, this is a little bit of a confusing current source symbol, so I'll just, okay. So this, instead of being 131 ohms, should just be 31 ohms, I think. And so then that means our predicted differential gain is what, like 5K over 62. That's like 81. I don't think we're going to get that high, but okay. So our predicted differential gain is now like something like 80. So let's see, oh, let's do it, and then let's see what we get. So here they are. So we have this 100 ohm resistor and this 100 ohm resistor. Those go, see you later. And so that means that pin 4 can be directly wired to pin 2. And then this current source can go directly to pin 2. Good. Ah, okay. And our differential signal. Oh, now you want, let's make it so you can see it. Okay, our differential signal got bigger. Now we have to do this in a way that we can actually measure a sensible gain. So let's go to WaveGen and make this like 10 millivolts. Whoops. Let's make this 10 millivolts and 10 millivolts. This is a 20 millivolt differential signal. 10 millivolts and 10 millivolts. And we'll come over here. Oh, okay. So that's a 20 millivolt differential signal, and the output that we see is, oh, so here, channel 1. And let's make our hysteresis a little bigger. Get a stable trigger. Okay. Seems like 1.2 volts. Yeah. Okay. So we have like 1.2 volts for an 0.020 volt differential signal. That's like, yeah, 60. I saw something similar to that yesterday. So, okay. What I'm able to measure is like a differential gain of 60. I predicted 80. I think if we really made the input signal tiny, so the small signal approximation is still good. The approximation you make is that VBE stays pretty constant. Then we could get, would probably get closer to our calculation. But anyway, good enough. We boosted the differential gain a lot. Okay, now we're going to unboost it a little bit. So the way we're going to do that is, it turns out that, so see, this is 9 volts minus 5 times 0.8. So this is 9 minus 4 is 5 volts. So 5 volts output. We're going to add our next stage. Here, let's just draw the next stage. Oh, but before that, let's do a little foreshadowing. So we are going to replace this resistor with 1.5 kilo ohms. So this 5 kilo ohms will, in just a moment, become 1.5 kilo ohms. And then our predicted differential gain will be 1.5, 1500 over 62. Oops. 24. Okay, so we'll see what happens. Okay. Why? Why are we doing that? Okay, so so the common mode gain is just very small. So it's going to stay very small. It's small enough that we just don't care about it anymore. Okay, so then we think that the differential gain, where are we going to put that? Should be something like 1.5 kilo ohms over 2 times 31 ohms is like 24. Okay. Why are we doing that? Because here, let me write this. This is IC is like 0.8 milliamps. So we're going to put a common emitter amplifier over here. And it's going to be an upside down one because we're going to use a PNP transistor. This is a kind of a cool trick. So there will be an emitter resistor. To make sure I don't use the same names too many times. Oh, and I think we even gave this a name as RE5 or something. Well, we called it RE2 on that schematic. That's unfortunate. Okay. Well, we'll just call it RE for now. And then this is a PNP transistor, so the arrow goes the other way. And then this is RC, which is going to be, and this is going to be 6 kilo ohms, which is a different value from what was in the original. So this is, and this is going to be 300 ohms. Okay. And then here's the base. And this base goes over to the output of stage 1. Yeah. So here is the output of stage 1 is the input of stage 2. All right, that's good. And then this goes all the way down to our negative power supply. So here's our negative power supply. I'm going to erase some of these details. And here we are. Okay, good. So the stage 2 gain should be minus RC over RE. In this case, this emitter resistor is big enough that little RE is pretty much unimportant. Okay, but we want the quiescent current through this amplifier to be reasonable. Reasonable is probably like in the 1/2 to 2 milliamp range. So that means we want the quiescent base voltage here to be something reasonable. Well, and actually not only that, it has to be reasonable so that the output of stage 2 is, we actually want the output of stage 2 to be pretty close to 0 volts because this will be pretty close to the level. We're going to follow this with a push-pull buffer, so we want this to be pretty close to 0 volts. So that's an important constraint. Okay, so if we leave this at 5, see if this is at 5 volts, now we would have like, so this is a difference of 4 volts. So this would be a difference of 3.3 volts. That would be like 10 milliamps collector current. Yeah, and that would be an awful lot, right? So in 10 milliamps, that would be like 60 volts, is that right? Yeah, is that really right? Anyway, so this is not going to work. So instead, we're going to make this 1.5 kilo ohms. Okay, so this now becomes 1.5 kilo ohms. That does reduce the gain from like 80 to like 24, the calculated gain. But now this, okay, right. So then this quiescent voltage here at the input to stage 2, VCC minus IC RC2, IC2 RC2 is 9 volts minus 1.5 times 0.8. So 9.0 minus 1.5 times 0.8 That's 7.8 volts. Okay. And then you say, okay, that's 7.8 volts. So then its emitter, this is a PNP, so its emitter is a diode drop higher. So then we're going to say plus 0.7 volts. That's 8.5 volts. Right. So now this is 8.5 volts. So that's a half of a volt drop across 300 ohms. So that's 500 millivolts divided by 300 ohms is 1.7 milliamps. So this should be like 1.7 milliamps. So then that's basically the same current here. The base current is much smaller than the collector current is about the same as the emitter current. So now you have 1.7 milliamps times 6 kilo ohms. So that's 10 volts. That's actually just about right. So that puts this output at about plus 1 volt. You want it to be 0 volts, but plus 1 volt's pretty good. So you see 1.7 milliamps. Here's our 6 kilo ohm. So this output then rests right around a volt. We'd really like it to rest right around 0 volts, but 1 volt is good enough for us. We wanted to use parts that are in your kit. Okay, so now meanwhile, we have a stage 1 differential gain of 24. Our stage 2 gain, here we don't need this anymore. Our stage 2 gain should be here minus RC over RE. So it's minus 6 kilo ohms over 300 ohms. So that's like minus 20. Okay, so then stage 2 gain minus 20, stage 1 differential gain of 24. So it's overall a gain of about 480. I think I saw more like 250 when I measured it yesterday. Although I did see, I think in circuit lab it was fine. And then because this is inverting, now which one of these inputs is called the positive input and which one's the negative input will be swapped because we added an overall minus sign. So which one we're calling inverting and non-inverting up here got swapped back and forth. Okay, so let's build this. Oh, and where are we going to build this? We're going to build this with pins 10, 11, 12. Yeah. Okay, so this is 10, 11, and 12. I had that wired up yesterday. I took it apart so I could go back through it step by step. So I'm going to wire this and then we'll test it. Okay, so I have stage 2 built now. There actually was a little pause when I forgot momentarily to replace this 5K resistor with a 1.5K resistor. That was fun. It was interesting to track that down. I noticed that this output voltage of stage 2 was at the wrong place when there was no signal present. Okay, so then we can look, let's first look at the quiescent conditions. So we can see that the output of stage 1 is at 7.97 volts. And I think, what did we, 1.5 kilo ohms times 0.8 milliamps. Okay, I guess I would have predicted 7.8 volts, and I see 7.97, but okay. And then the output, remember we predicted that this would be about 1.7 milliamps, so then this would be about plus 1 volt. Instead, I get about minus 1 volt, so I think this current must be a little, let's see. Okay. Here, let's just think about this. So this difference is 1 volt. So then this is like 0.3, so this is like 1, is that right? This is like 1 milliamp. So this is like 1 milliamp, I guess. It doesn't quite make sense. It should be a little more than a milliamp. Okay. I guess depending on exactly where this base lands, that will have a significant effect on this quiescent emitter current, which will then have a significant effect on this output voltage. So I was expecting this to be, we want it close to 0. I was expecting it to be about plus 1 volt, and what I see is about minus 1 volt. So in any case, we succeeded at putting it pretty close to 0. But I think, you know, where exactly it lands will depend in detail on this quiescent current, which will depend in detail on this quiescent base voltage. Okay, anyway, it's pretty good. And you can check the circuit lab model, but actually everything works out quite nicely in the circuit lab model. So now let's add a signal. So this is a 20 millivolt amplitude differential signal. And then we'll look and see what we get. And these are both on 2 volts per division. So there's the output of stage 1 and the yellow trace near the top. And then the output of stage 2 is the blue or cyan trace near the bottom. And then let's see if we can. So I'm doing this assuming that I'm actually dragging a channel 1 cursor around to look at channel 2, but they have the same scale and the same offset, so I think we're okay. So this seems like okay, so it seems like the offset actually is a little more than a volt, but anyway, it's on the order of a volt. Okay, so 3.41, 6.52 here. So 3.41 plus 6.52 divided by 2. That's the amplitude. And then meanwhile, right, 3.41, 6.52. And then let's look at, this is a 20 millivolt amplitude differential signal divided by 0.020. So that's, yeah, like 250. Okay, so I see like an overall differential gain of about 250. The calculation was more like 480. And I think it was closer to expectation in Circuit Lab. So it may be that I'm not able to put in quite small enough a signal here to be able to get a really good. Here, let me do just, I can pull out 1/2 of this thing. Yeah, I can ground one of these inputs. So now it's kind of a pseudo differential signal. And I can also make, that's interesting, I get such a big offset there. And then I can make the differential signal even a little, well, actually 10 millivolts is about as small as it gets. Okay. Huh. Gee, what if I do the other way? So I can ground the other one. Let's see what happens then. So I'll put this one back. And I'll ground the other one. Huh. So it's a 10 millivolt differential input signal. And I don't have a great measurement here, but let's see. 5, I think it's about the same answer though. 5.3 minus 3.36. Okay, divided by 0.010. That's like 200. Yeah, okay. So I seem to see differential gain of something like 250 when I was predicting something more like 480. Huh. I hope that doesn't mean that half of my differential amplifier is not working. Let me try a common mode signal. Make sure the output is still small. Yeah, okay, look at that. Cool. Common mode signal, the output is tiny. Good. Okay, well, I think we're going to declare victory on that. So that was stage 2. Let's go back to a differential signal. Oh, now I think we can get rid of some of this fuzz, because I think stage 2 oscillates a little bit, and there's a little piece of wisdom later on. We can add a little capacitor between the base and collector of stage 2 here. So if we put a 100 picofarad capacitor, that kills the high frequency gain of stage 2, and it should get rid of a lot of that fuzz. And I happen to have a 100 picofarad capacitor here because I was using it yesterday. Let's see if it miraculously gets rid of that fuzz. Between pins 11 and 12, 9, 10, 11, 12, 9, 10, 11, 12, 9, 10, 11, 12. Oh, look at that. Yeah, nice. So we got rid of a lot of that fuzz with this 100 picofarad capacitor between pins 11 and 12. This exploits the so-called Miller effect. You can look that up, Miller effect, to kill the high frequency gain of this amplifier. It's basically a form of negative feedback. And actually, now let's take a closer look at what we get here for the overall gain. So, actually, why? See this little flat spot? I'm a little suspicious of that little flat spot. I wonder if this thing will do 5 millivolts. No. Okay. What happens if I make it a pseudo differential signal? Oh, that's actually not bad. No. Oh, I see. To ground it. Okay. Well, you're listening to me talk aloud, you think aloud. So I guess it didn't change things much. Okay. Right. So 5.99, 2.64. They're opposite signs. 5.99 plus 2.64. Divide by 2 to get the amplitude. Divide by 0.020, which was the input amplitude. 215. All right. Well, anyway, that's a decently big differential gain. Okay, then we want to move on to stage 3, which is a push-pull buffer. And the way we do that is we are going to, okay, so this amplifier has an output resistance on the order of 6 kilo ohms, okay, because this collector resistor sort of dominates the output resistance of this common emitter amplifier. So that's not a very good output. We want a much smaller output resistance. So we can get an output resistance smaller by a factor of roughly beta. So instead of like 6 kilo ohms, it could be like on the order of tens of ohms. If we put some kind of emitter follower, and our favorite kind of emitter follower to follow a bipolar signal is a push-pull. So we will take our push-pull. It's just so much fun. So we have a NPN transistor to follow the positive excursions. Oh, there's my meter. And we have a PNP transistor to follow the negative excursions. And there we go. And then we connect the two bases together. And now this is the new output of the overall circuit. And then we connect the output of stage 2 to the input of stage 3. Okay, so remember, this is NPN, this is PNP. So this is collector, base, emitter. This is emitter, base, collector. And then, where are we going to wire this up? We are going to wire this up using pins. Okay, this is 7, 8, 9. So here is 7, 8, 9. And this is pins 13. Again, we have Tom Hayes to thank for this design. 14, 15. Okay. Let me wire that up. It won't be too exciting initially, and then when we connect it with feedback, it will be exciting. So here we go. Okay, I have added the push-pull. I guess I'll try to give you a tour of the whole circuit in a moment, but let's see this thing working. So I have scope channel 1 looking at the, let me just shove this over a little bit. I guess that's all right. Okay. I guess it's okay. All right. Scope channel 1 in yellow is looking at the output of stage 1. So that is here. Scope channel 2 in cyan or blue is looking at the output of stage 2. So that's here. And scope channel 3 or magenta is looking at the output of stage 3. That's here. And one thing that's kind of cool is you can see the crossover distortion where the output of stage 3 passes 0. So that's kind of neat to see. And then the next thing I want to do is connect this thing in a loop with negative feedback. And we'll see it work as a times 11 non-inverting amplifier and as a times 10 inverting amplifier. So I think I'm going to cut the video and then I'll start a new segment and I'll give you the grand tour going around like this rat's nest, and then I will wire up the circuit with feedback to see how it actually works as an op-amp. So this was our baby op-amp. So of course you don't really know if it's doing anything useful until you try it with negative feedback. So it worked yesterday, so we'll do that in a moment.